Yes, class. Hello, is this audible to you people?
Yes.
All right.
Yes, ma'am.
Okay. See, in the last class, we had started with identical cells combination. Series combination, we have already discussed. So, in series combination, what happened? Equivalent resistance was given by adding all the EMFs that were present. So, if n number of cells were there, n times E will become your E equivalent. Then we had seen current and we had seen two cases. If external resistor is greater than internal resistor, and if your internal resistor is greater than your external resistor, what is the final formula that you get? Now let's start with parallel combination. So parallel combination, see, number of cells in a single row will remain the same, but number of rows will be different because they are connected in parallel. So let's say this is first row, this is second row, up till you have m number of rows. Because just to differentiate between m and m, otherwise we'll get confused, no, if we have m and both together. So let's just write it as m. So m means the identical cells. M are the identical cells that are parallel, that are connected parallel together. Now, can anyone tell the equivalent EMF? Each cell is having EMF E. M number of rows are there. Can you all tell me what is the equivalent EMF? Just write it
E
in the
plus
chat
E
box.
plus E.
E plus E plus E. So what will it be, Khalid?
3E.
M number of
N.
rows are there. Yes, there.
Ma'am, NE.
ME.
Yes.
All. See, though M number of cells are there, M number of rows are there, each row is having E, one cell. So E plus E shouldn't be the case in this combination. NE, if n rows are there, NE, no. See, this connection is parallel. Do you remember which 3E? No, Khalid. See, if in parallel combination, if you remember, one quantity that remains the same is potential. So EMF, however number of cells you connect, the EMF for the whole equivalent combination, that will still be E only. Remember, in this we had discussed, in case of series, current or charge remain the same. In case of parallel, the potential or the EMF remains the same. So even if m number of identical cells are connected in parallel, the equivalent EMF will still be E. Now, equivalent internal resistance. Can you tell me this? Anyone? Equivalent internal resistance. Each one is having resistance small r. Internal resistance. Anyone? Look at it, small r are connected. 3R, how can you add them directly? They are not connected in series, no Khalid, they are connected in parallel. Keep this in mind whenever you're doing the calculations. In series, we directly add, no, the resistors R1 plus R2 plus R3. Here, in parallel combination, you write it as R1 by R equivalent. No, forgot. 1 by R plus 1 by R till whatever. If m number of rows are there, it will be m divided by small r. So R equivalent will be what? R equivalent will be small r divided by m. This is the value of equivalent resistance that you have. You have the value of EMF. So this is current you're writing, Hania.
Yes, ma'am.
See, m will also be there, no? Because right now small r is having m getting divided. Now try it. See whatever is the correct current. See, normal formula we know, I is equal to EMF. EMF is what? E divided by internal resistance plus external resistor. R equivalent is what? R by M plus external resistor. So if you take the LCM, this gets multiplied by M and the denominator M can be transported in the numerator. So current ultimately becomes what? ME divided by small r plus M into capital R. This is the formula of current that we get. Now both the two cases that are there. I is equal to EM plus R. This will also be there. No, see, when you take the LCM, this will get multiplied by small m. So one small m will be here as well. Now the two cases that we had discussed in the last class as well. Two cases when your external resistor is greater than your internal resistor. When your internal resistor is greater than your internal resistor, it means capital R value is huge. We are taking the numerator as what? We are taking the numerator as MR plus small r. Now this term is huge. This is let's take the example again, the way we had taken it in the last class. This is 1000 and this will be approximately 0.5 or let's say 1. So even if you add 1001, that gives you 1001, which is approximately equal to 1000 back. So in a huge quantity, if you're adding a small resistance, that gives you small value of capital R multiplied by M back. So how can you write the denominator? You can write the denominator instead of this whole thing. You can just write MR. Here, you can just write MR. Now, one more thing. In this case, when capital R is greater than this, your small r, if your capital R, this is so much huge than your capital, this near your small r, then we take the number of rows as well. For this is for a single row. Then you take it for the number of rows. So here your mm will get cancelled and your final answer will be capital E divided by capital R. So the equivalent resistance, because it is parallel combination, it will be E. So whenever you are using the formula, use this one only. ME divided by small r divided by MR. In this case, what is happening? In this case, we are taking equivalent resistance where external resistor is greater than small r. So what is happening? We are considering it for each row. So M gets multiplied. We are not taking E equivalent as ME. We are multiplying M to the whole current that we are getting. And second case was what? When your internal resistor is greater than external resistor. So in this case, can you tell if MR plus small r is there? How can we approximate it? See, MR plus R will be approximately equal to what? If your internal resistor is greater than your external resistor. Yes, Hania, can you try? If your internal resistor, this is greater than your external resistor.
I is equal to E by MR.
E by MR, not the whole formula. Okay, Samaira is right. See, I was asking you just this. How can you approximate it? Like the way we have approximated this whole term into MR, how can we approximate this? See, this is a huge term. This is very large and this is a smaller term. So if you add a very small quantity to this huge quantity, this time small r will be having the greater power. This will dominate and we can approximate the denominator into r. Now, as the formula said, again repeating this, ME here is not E equivalent. This is this formula only. This ME that we are getting on taking the LCM. So again, we'll put it as ME divided by. Instead of R plus MR, what should we write? We should write only small. So this is the formula that we get. Now, one more important point that is left to discuss is when to prefer parallel combination, when to prefer series combination. Because we'll do a question also there, I'll give you this part only. When you have parallel combination, when you prefer parallel combination, when your internal resistance is large as compared to your external resistor. Here in this case, you prefer parallel combination because you're getting a higher value of current. Here it is only E by capital R. Here it is ME divided by R. See, conditions can vary. It can also have a higher value if the values change of capital R or something. But in general, if nothing is mentioned, we prefer parallel combination if the internal resistance is greater than external resistor. In series combination, where your external resistor was greater than internal resistor, this case, here we prefer series combination. series combination is used to calculate the answer. So this preference and how to choose this, that will get only clear when we do the numerical. So I'll give you a numerical on this. First, just note down these points. Then let's do a question. See, this question says 8 identical cells of EMF 2 volt each. These are connected to external resistor of 0.05 ohm first, and then the external resistor is having the value 100 ohms. Internal resistance is given to you as 1 ohm, and you have to decide which combination you would prefer. Means here nothing is mentioned, no, whether it is series combination or parallel combination. So that decision, that whether it is parallel or series, just you can take with the help of the value of internal resistance and external resistance. But you don't have to calculate that maximum current. Calculate the normal current using the general formula. Don't use these formula, whatever preference you are taking for whichever combination. Use the main formula for it. At least try the first part and let me know your answer, then we'll discuss. All of you try this at least. Sneha, are you able to understand all of these? Just two small topics select, then we'll begin with chapter 4. Yes, combination you have taken correctly. First one, both you have written first. Okay, second. First one, this combination. Second one, this combination. Fine, fine. Combinations are correct. Now use the normal formula for calculation of your formula of current. You have to calculate the current. Had it been asking you the value of maximum current, then you would have used those formula. When we have approximately taken the value. Since nothing is given right now, you're not asking the maximum current, normal current you have to calculate. So use the main formula. ME1, NE1, those formula for parallel combination and series combination. Whichever combination you think is the answer. So parallel understanding and deciding parallel or series combination is first you are concerned right now. Then whatever is the formula, solve it accordingly. Yes, Salman. Correct, correct. Now you know the formula for it, the general formula for current for each of the combinations. Put it, see what's the value you're getting. Good, Samira. Correct. Right. See, external resistor is 0.05 ohms. For the A part, see external resistor is what? 0.05 ohms. Small r is what? Small r is 1 ohm. This is comparatively a bigger number. Small r is greater than capital R. Which combination is this? Right now I've told you this combination which you have written. This is parallel combination. So you prefer parallel combination. So the formula in parallel combination is what? M multiplied by E divided by R plus M into capital R. M value, number of identical cells that are given is 8. So current becomes what? 8 into EMF. EMF is 2 volts. Small r is 1 plus M is again 8 multiplied by capital R, that is 0.05. So solving this, you will get the answer around 11.42 amperes. This will be the answer for the first part. Now regarding the second part, everything remains the same except for the value of external resistor. External resistor this time is 100 ohms. Small r is still 1 ohm. See, now capital R is so much greater than small r. 101 is approximately equal to 100 only. This is which combination? This is series combination preference. So what was the formula in series combination that we saw? NE divided by N small r plus capital R. Now number of cells here is 8 only. For both the parts you have 8. So N also becomes 8. Here M was 8. Here N will become 8 because both of them are same. No, nothing is mentioned especially for number of rows and number of cells. Right now 8 identical cells are connected. Only this much is clear. So they are for the first part they are connected in rows. And for the second part, they are just connected in a single row. So I will be what? 8 multiplied by voltage is what? 2. Divided by N is again 8 into small r value is 1 plus capital R value is 100. So this is 16 divided by 108. That gives 0.148 amperes. Yeah, so note down the answer of both the parts. Okay, Zed. And what about others? Done? See, mixed grouping means what? Mixed grouping means you are having series combination as well, parallel combination. So here you just have to remember the formula. For remembering the formula, just note down one thing. In case of series combination, first solve it as series combination. For series combination, what will be the equivalent EMF? This is E plus E plus E. So n number of identical cells are connected. So it will be what? It will be NE. So you have NE for as a, after solving this, here you will have NE and you will have R. Then you will solve this row also. You will get E, NE, and small r will be there. Not only small r plus small r plus small r, this all will get added. So small r getting added together, this will give what? This will give n into small r. And this gives n into small r. Similarly, for this row also you have n into small r and n into capital. So this will be your equivalent resistance, equivalent circuit right now. External resistor capital R, NE, 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 all are connected in parallel. We have reduced this circuit by solving each of these. See, first we had solved this entire row. Then we have solved this entire and we have reduced this in terms of this. Like this, we have reduced our total circuit. So now you have parallel combination. How do we write the parallel combination? Remember, equivalent EMF will still be the same. Equivalent EMF will be equal to N times Z, because NE is a value for each cell. For all the cells, it will be NE. For internal resistance, you will be having 1 by R equivalent. It will be written as 1 by small r, NR plus 1 by NR up till M times by NR. So R equivalent becomes what? NR divided by N. All the steps are similar. It's just that N and M together will come. Both of these will together come. So I will be equal to what? E equivalent is NE. Small r is written as NR by M plus capital R is there. So if you take the LCM, this becomes N into M into E. Here you have NR, here you have M. Just to avoid the confusion, I am writing M is the number of rows. N is the number of cells in a row. Capital R is external resistance, E is the EMF. If you get somewhere, no, what is the maximum current or something related to maximum current? Remember, current is maximum if N into small r is approximately equal to M into capital R. There you can say, if you have such a condition, then you can say your current in the circuit is maximum. And one more point as well, one more thing before you note this down, because this is the derivation and complete formula for it. One more thing that was left was heating effect. So heating effect of current also has a single formula. Heating effect of current. One formula was there. So see, whenever current passes through resistor, part of electrical energy is dissipated as heat. That's why we study heating effect of current. So heat dissipated per unit time, we call it as power. Power becomes what? Heat dissipated per unit time. Also the formula, direct formula come in your exam, it is I square R, or it can also be written as V squared divided by R, or it is also written as V by I. All the three are same. Remember the way we had energy for capacitance, it was half CV square, it was Q square by 2C, it was including all three of it. H is equal to I square RT. Yes, that is also there. That is heat. Heat will directly be I square RT. Because the heat is what? Heat is power multiplied by time. Power is I square R. This is power. And time is T. So heat becomes I square RT. So this is the formula. And SI unit of power is, this was the small topic was left earlier when you were discussing. All right. So note this down as well and text me done so that we can start with the next chapter. Just text me done when all you have written.
Ma'am, what is heat again?
Heat.
Yes.
See,
Heating effect.
whenever current passes through a resistor, all right, whenever current is passing, electrical energy we have studied. Remember, electrostatic energy, electrical energy. We had seen different formula for electrical energy. All that electrical energy, not all of the electric energy, but some of the electric energy dissipates, and it gets dissipated in the form of heat. So you must have seen whenever you have charged your mobile phones, the wire of the charger that becomes hot, or if you have connected a charger to your laptop, or if you have connected any instrument, wire always becomes hot. This is because of the heating effect of current. So whatever heat is there, when it gets dissipated for 1 second, we call it as power. All the heat that dissipates for 1 second, we call it as power. So whenever current rushes in through the wires or through the resistors, part of the electrical energy that dissipates as heat. So heat will be equal to power multiplied by time, and power will be equal to heat divided by time. And 1 joules per second is known as watt, which we write it as W capital W watt capital W. That shows power. So power is basically heat for 1 second. Whatever heat has dissipated for 1 second, that is power. And heat is what? Heat is the part of electrical energy that has gone wasted. The loss of energy, basically. So, yeah, Khalid.
Yes, teacher.
None others apart from these two, Sumaira and Zaid.
Done, ma'am.
Okay, Salman, fine. All those who are having the mass time over there, you can go for your numbers. This and the previous one means chapter 2 and chapter 3, Zaid.
Yes, ma'am.
Of course, I will.
Okay.
Now, your chapter number 4 of NCERT, that is your magnetic effects of current. So this becomes from here, your electromagnetism portion is divided into two parts, no? Electrostatic portion and your current electricity portion. And second one is your magnetism. Then you have combinations of both of these, and you will be seeing everything that gets repeated in both of these chapters. You have chapter number 5 also, no? That's a very short chapter. That's exact replica of whatever you studied in electric field. All the formula for equatorial line, for axial line, everything gets repeated in your chapter number 5 as well. So whatever you have studied, that will be utilized, but understanding your concept portion becomes easier here, because field, concept of field, you people are aware of. So you had what? You had electric field when we were discussing electrostatics. Electric field we had discussed in detail. We had the half chapter for electric field only. So if you have forgotten, electric field is the space around a charge where electrical properties existed. Now here, analog of electric field, you have magnetic field. So concept of field, imagining the concept of field is now not tougher for you people. If it was the space around a charge, electric field was the space around a charge. Magnetic field will be what? One more thing. Sneha, in your school is current electricity completed? Whole chapter?
Yes, ma'am.
And chapter 1 and 2 are also completed?
Yes, ma'am.
All right, fine. So that's why I was just asking so that you will be able to relate it. So electric field was what? That was the space around the charge. Magnetic field, this will be the space around the magnet. All the concepts of charge will get, like for positive charges, for negative charges, we have these two names, positive and negative. Here we'll be using North Pole, South Pole. Though North Pole and South Pole are not charges. We are just relating it the way whatever you have studied in electrostatics. No, now understanding of concepts is easier in magnetics whenever you study magnetism. No, so similarly, it is the space around the magnet. Now, what happened in case of electric field? It was the space around a charge where electrical properties existed. We could feel the force of attraction or repulsion, no, whenever the test charge was brought towards the source charge. Similarly, it is the space around a magnet where magnetic properties can be felt. Salman, you have submitted one assignment, no? I think it's yours or something. Recently, you have submitted an assignment, no, Salman?
Which one, ma'am? Like today expiring one?
In your current electricity only. I'm not able to remember it, but I just wanted to confirm whether it was you or Khalid. Recently. Kirchhoff's law, no?
Yeah.
Okay. So, because only you were there who has submitted that assignment. None other student had submitted that.
Yeah, I was gonna submit today, but I'm not feeling well.
All right, fine. Your that Learnivio portal is working now, no? Are you people able to upload your assignments?
Yeah, we can.
Only Salman knows because he has tried to upload it. So magnetic field is what? It is the space around a magnet where magnetic properties exist. So easy, similar to whatever you have studied now. So let's take example. See, this is a magnet. This is a typical bar magnet that I have taken. The way, if you remember, charge had this space. And if you bring any charge over here, small charge, then you can feel this forces of repulsion or attraction. Similarly, electric field was also property of a single charge. But see, magnetic field, this is a property of north and south pole combined together, not a solo charge, because monopoles do not exist. That we'll study. When we'll study magnetic dipoles, everything gets repeated in magnetism. Like you had electric dipole, you'll be having magnetic dipole and everything. So there we'll see. But right now I'll tell you, even if you cut this magnet, if you cut this magnet from the middle, this portion will develop south pole, this portion will develop north pole. Monopoles never exist, means a single pole. So just for your, now if this is a bar magnet, so it will be exerting this certain field. There will be a magnetic field around, which will be initiating from the north pole. It will get completed and form a complete closed loop. The properties we'll see, don't worry about the properties. And again, it will terminate from the north pole, begin from the north pole and terminate at the south pole. This is your concept of magnetic field. Now, the way we had magnetic flux, magnetic field strength, magnetic flux density, electric field flux, then electric field strength, electric field intensity. Similarly, we'll be having magnetic field strength, in magnetic intensity, magnetic flux density, and others phenomena associated with it. Now, magnetic field is represented by this symbol B. B. The way we had electric field as capital E, you have magnetic field as B. This is the symbol for magnetic field. And obviously, magnetic field is also a vector quantity. We have so much laws for it, for the calculation of magnetic field. Not only in your 12th standard, in your earlier classes as well. I believe in 10th standard also you had these laws, Fleming's right-hand rule and all these laws for calculation of the direction. So obviously, this is a vector quantity. That's why I'm representing it through this arrow on the top. This is the symbol for magnetic field. SI unit for magnetic field is Tesla, which is represented through capital T. So you will get the values of magnetic field like this: 4 Tesla, 5 microtesla in this way. This is the SI unit. Does anyone know what's the CGS unit? CGS unit, this is Gauss. Gauss is the CGS unit. Now conversions do come. So be careful with the CGS unit and the SI unit. The conversion is 1 Tesla is equal to 10 to the power 4 Gauss. So many a times it is written in terms of Gauss. So you have to multiply it with 10 to the power minus 4. If it is written in terms of Tesla, then if it is written in terms of Tesla, then no need, because Tesla is already a standard international unit, SI unit. One more thing before moving on to the main topic that we have, sources of magnetic field that are possible. Sources of magnetic field. From where can you get magnetic field? So can you people suggest what should be the sources of magnetic field according to you people? See, the iron, the mineral iron that is there, hematite iron that is there, that also produces magnetic field. Apart from it, you have current carrying wire. The current carrying wire also produces, we'll see how a current carrying wire produces magnetic field. Then you have simple magnets that exist in nature, like a bar magnet is there. All the magnets that exist in nature. So bar magnets are there, different horseshoe magnets are there, different magnets are there that exist. And then you have a device known as solenoid. For solenoid, you have a whole derivation, whole numericals to come. That is formed by coiling and a magnet is inserted, that you see. So solenoid is also there. Another instrument is there that is known as toroid. Then intrinsic spin, in electronic spin. If you remember, I think in your 11th standard, this is included in your chemistry. Remember some magnetic spin, minus half, plus half of an electron.
Yes.
Yes, you must have done. Where I think you had to calculate everything: spin, magnetic spin, and different valence electrons and all those things. I think this question comes in from your periodic table, something in your 11. So this also in intrinsic electronic spin. Intrinsic electronic spin. This is also one of the causes of magnetic fields. So before moving on to the major law, the way we had Coulomb's law over there, we have Biot-Savart's law over here. That we'll see, but first I would suggest you people to note down this. And always remember that conversion, Tesla and Gauss. Because in case of electric charge, or when we discuss electric charge, everything is usually given in terms of Coulomb. Coulomb is there, microcoulomb, nanocoulomb, picocoulomb will be there, but Coulomb is usually written in case of charges. But in case of Tesla, these magnetic fields, Gauss is also written many times. So this is an important conversion. And the major confusion comes whether it is 1 Tesla equals to 10 to the power 4 Gauss, or whether it is 1 Tesla equals to 10 to the power minus 4 Gauss. Yes, sir, that is 1 Tesla. 1 Gauss will be equal to 10 to the power minus 4 Tesla. Both the conversions you people show. This is an important conversion. This gets utilized.
Ma'am, by the way, what did you write in the first point? Sources of magnetic field.
sources of intrinsic electronic spin, this one that I was mentioning you. Minus half plus half electron spin, no, that when electron spin, that produces magnetic field. We'll see motion of electron that produces how it will produce magnetic field. And this topic, this will exceed until EMI also, electromagnetic induction. Okay, I'm scrolling up, just a second. Oh, which one said Oersted's experiment? Okay, Oersted's experiment. Yes, actually, that experiment that is not included in your syllabus. Means you don't have to actually perform the experiment. But I'll discuss it. I'll discuss the experiment. That actually led to the discovery of magnetic effect of current. And then you have Ampere swimming rule as well. But Ampere swimming rule, we won't go into that. Ampere swimming rule, that was lot apart from the syllabus. Before starting or beginning with Biot's law, let me just discuss that experiment which Zed was mentioning. See, a magnetic needle was pivoted over a stand. All right, and a needle was held through it. Let me draw a brief diagram for it. See, in this way, a stand was there, a needle was there. One end was shaded, which we called it as the North Pole. Other end was there, which we had the South Pole, and the whole circuit was also placed. Like this. So a magnetic needle, this SN, we can call it as SN, this was pivoted over a stand. And a wire, this was parallel to the needle and it was connected to the cell. And this key was there. All right. Now, what was the observation? Observation was that when the wire is held above the needle, all right, and current flows from south to north. So when the wire was held above the needle and the current flows from south to north. This occurs south to north. Then what was observed? That the north pole of the magnetic needle gets deflected towards the west. The needle of north pole, it gets deflected towards west. And when the direction of current was reversed, no, so that it flows from north to south, the north pole of the magnetic needle gets deflected towards the east. Like this. If this is the direction of flow of current, this is from south to north, and this will be the direction of north to south. So if this is north south, here it will be west, and here it will be here. And one more observation was there, that when the wire, this whole wire, this was placed below the needle, direction of deflection of the needle, that again reversed. And when the current finally got stopped flowing, then the magnetic needle came back to its original position. So since a magnetic needle can be deflected by a magnetic field only, it follows from this whole above experiment. This shows that what? That a current carrying conductor produces a magnetic field around it. So this point that I was mentioning, this current carrying conductor produces a magnetic field. So the explanation for this was given by this Oersted experiment. So don't worry about this experiment. No need to learn this experiment. It's just that one of the students wanted to start with it. That's why we began with it. Now we have one more law to calculate or basically to explain whatever is the magnetic field. So Oersted experiment showed that a current carrying conductor produces a magnetic field around it. So it is convenient to assume that this field is made of contributions from different segments of a conductor, which you called as the current element. Current element will be utilized here in this Biot Savart. So I'll tell you what again is a current element. Biot Savart law. See, it says that, let's say this is your wire. It is having current flowing, I current is flowing through it, and I have taken a random P point. Random P point I have taken. Here I have to calculate what is the magnetic field. See, Coulomb's law gave you the value of force. Biot Savart law doesn't give you the value of magnetic force. It gives you the value of magnetic field. So remember, Biot Savart law, which we are discussing, this is for calculation of magnetic field. Now, what is this law? First, you have to understand what are all the things that are included in this. Firstly, from a wire, current I is flowing in this way, in this manner. And remember, Biot and Savart, these are name of two scientists. Two scientists were there. Some Jean Biot and Felix Savart. These were kind of name. I don't remember it clearly right now. These were two scientists who gave this. They deduced the expression for the magnetic field, which ultimately became the Biot Savart law, which is known today. So if I take this point P, all right, I'm taking a point P. Let's say this point P, this is separated by small r. This is what? This is the position vector. Small r is the position vector of this point P. It's the position vector telling you the position from this wire. Now I have taken a very small portion dl. This is called as the current element, which I was telling you. A current element is basically what? See, this field, whatever field is there, magnetic field, it is made up of contributions from different segments, which we call these segments of a conductor as a current element. Means we have just taken a small portion from the whole wire, no, where the whole current is flowing. I have just taken a smaller portion. And by convention, this is named as a current element. And DL is represented as a current element. And since it's a part of this wire only, so the direction of the current is same as the direction of P. All right, from this, since this is the direction of current and we have taken a smaller portion of the current element only, so that's why direction becomes same. Now we have to calculate what? We have to find out whatever is the magnetic field at this point P. magnetic field at P due to, and this law is very important. Your numerical, more than numericals, your whole derivation is based on this law. Most of the derivations of this chapter, you will be having, the way you remember for Gauss theorem, we had different shapes. We had infinite plane sheet, we had a long wire, we had different cases as the application. So application of Biot-Savart's law is important because this will be utilized. That's why I listen it carefully. So magnetic field at P due to current element dl. Current element dl. Again, always mention these small points whenever you are performing your calculations. I'll discuss the paper also right now. Four students were there, no? Salman, see again. Now your paper is better. Everything is, you have written it correctly. But just again, see, you have to define all these terms. What all you have written. Where, what is this? Average relaxation time, you're taking it as 0. Initial velocity, you're writing as 0. What is capital E in this formula? What is ME? Is it mass of conductor or is it mass of electron? No. So just specify. Same with, I think, Khalid as well. Yes, you have to define the terms. Rest of the things was fine. Zaid also gave the term. Zaid, when these are such questions, don't leave it in terms of fractional value. Zaid has done the derivation perfectly. Zaid gave the derivation well. Due to this, it happened. You have to consider it. This is how you write your derivations. Then you get your full score. But in case whenever you're giving an answer, 190 divided by 30, it's a complete answer. You get 5 ampere. So don't leave it in terms of decimal unless specified. Memona is absent today, no? Memona also gave the test. All right, so this discussion was there. Before I forget, that's why I discussed this. Yes. So where were we? We were discussing Biot-Savart's law. All right. So we are calculating magnetic field at this point P due to the current element dl. Now, one more thing we have to define, that is this angle theta. This theta is what? This is the angle between this current element and this position vector r. So this is the angle between dl, means the current element, and small r. Now, your law becomes, what's your, we have defined all the terms, we have understood each of the term. Now, according to Biot-Savart's law, according to Biot-Savart's law, since we have taken small portion of current element, no, that's why I'm writing dB. So dB, your magnitude of field dB, this is firstly directly proportional to the current through the conductor. First point of this law. Second point of this law, your magnitude of magnetic field, this is directly proportional to the current element dl, length dl of the current element. Then thirdly, this dB, this is directly proportional to sine of the angle between the dl and small r, that is dB is directly proportional to sine theta. Fourth, like Coulomb's law, this is also inversely proportional to square of distance between the point and the element, current element that we have taken. So it is inversely proportional to the square of the distance r of the point P from the current element. Now, if I combine all these 4 factors, so on combining these 4 factors, dB is actually directly proportional to I, current, dl, current element, sine theta, angle between them, and inversely proportional to r square. Always we'll have a constant. In electrostatics, you had the constant 1 over 4 pi epsilon naught. Here also, you have a constant in magnetics, that is mu naught by 4 pi. This is the constant that you put, and rest of the things will remain the same. So this is your Biot-Savart's law that you get. Mu naught is different. See, it's not epsilon naught. It's the absolute permittivity of free space. In case of magnetics, means it will tell the effect of medium on a magnetic field. Let me write down this mu. Here it becomes absolute permittivity, or not permittivity, sorry, permeability. Permittivity was in your electrostatics. Absolute permeability of free space or air, whatever. The way we did no epsilon naught. Similarly, you have mu naught over here. And this shows what? This shows that if the effect of medium on magnetic field. This shows the effect of medium on magnetic field. So this is your Biot-Savart. Now, when we discussed Coulomb's law, when we were discussing Coulomb, see one relation similarity with Coulomb's law is that you have it is inversely proportional to R square, means it follows R square, inverse square rule. Gravitational force, your magnetic field, and your electric force. All these three are follow your inverse square. Now, when we were discussing electric force in Coulomb's law, we had seen if the medium was air, we used to keep it as epsilon naught. Remember, 1 over 4 pi epsilon naught Q1, Q2 divided by R square. But as soon as the medium changed, we multiplied this by K, whatever dielectric medium value was there. K is equal to 2, 3, 4. In capacitance also, we had seen dielectric constantly. So here, in case of magnetics for any other medium than free space. Free space means your air, vacuum, any free space. The way epsilon naught value was 8.85 into 10 to the power minus 12. Here also you are using mu naught. So in this case, if you have a different medium, multiply mu naught with mu r, which is the permeability, relative permeability of a medium. So if you multiply it, the whole formula will become this IDL sine theta divided by r square, and 4 pi also, no? So 4 pi r square. This becomes the formula if you have any other medium apart from free space. So just let me define what is mu r. Mu r is basically relative permeability. Relative permeability of medium. So you have different value of mu r. Mu r is there in your syllabus. Don't ignore this. You have chapter number 5, no, magnetism and matter. There for different substances, like you have ferromagnetic substance, which has certain properties. Their value of mu r is greater than 1. It's huge than 1. For iron, mu r value is approximately equal to 1000. For a diamagnetic substance, diamagnetic. For a diamagnetic substance. What are diamagnetic, ferromagnetic, ferrimagnetic, antiferromagnetic? All these you will study in the next chapter. Diamagnetic. For diamagnetic substances, mu r value is less than 1. All these things you will be studying, how it is related to mu naught, mu r, all these things. So right now, what's your major concern? You have to remember that according to Biot-Savart's law, the magnitude of magnetic field depends directly. It is directly proportional to the current flowing through the conductor. It is directly proportional to the length, dl length, that is the current element, directly proportional to sine theta. It is directly inversely proportional to r square, and the proportionality constant k depends on the medium between the observation point and the current element for the system of the units whichever is chosen. And k's value I'll discuss. K's value is there. You have a certain value of k, but before that, just note it down. The way you had 9 into 10 to the power 9. Here also you have certain value for the constant. Z, do you keep writing together when I'm teaching?
Yes, ma'am, sometimes.
See, whenever I'm speaking, I give you people so much time according to everyone's speed. Even if any student says to scroll up back, then I also scroll up. So it's better if you listen. If you listen in the class, then it's better, because sometimes it might happen that a point gets missed while writing it down. So once everyone is writing down, then note it down. You'll get sufficient time for it. All right, sir.
All right.
One more point of similarity is there between the coulombs, both the fields, electric field and magnetic field. Both are inversely proportional to square of distance between them. Other point is that both are long range forces. This is also one more point. Both are long range forces, and principle of superposition is applied to both of them. And differences are many differences are there. The direction of electrostatic field is along the displacement vector. Direction of magnetic field is perpendicular to the plane. Many differences are there. Electrostatic field is produced by a scalar source, which is the charge, but magnetic field is produced by a vector source, the current element. Current element is a vector. It's not current. It's a displacement. Whenever the derivation of this comes, or any derivation in physics, always write all the points. If you are short of time, you're running short of time, write it in this manner by making an arrow and writing whatever you have defined the terms. Otherwise, when you are having time, write the paper the way Zed gave. Zed's papers, that derivation was perfect. Everything was written. So consider a line segment for whatever derivation is there. If you have like capacitor's derivation is there, so you have to write, consider a parallel plate capacitor with area A, sigma as the surface charge density, like this. Everything you have to mention. Similarly, in Biot Savart also, current element is taken as DL, whose direction is same as that of the wire current that is flowing. R is the position vector of point P to the current element, and everything. Just mention. And if you're running short of time, at least at the end mention what is sine theta, what is R, everything. So the next test, whenever you will be having, most probably I'll let you know whenever the next subjective test that will occur. You will be having combined test of chapter 2 and chapter 3, means current, electricity and electric potential and capacitance. So start revising all these terms and don't forget your chapter 1 as well. Right now you don't have any test. Okay, Salman, take care of yourself. Fine. See, in vector form, if we write it down, in vector form, I think you people will be able to identify it easily. Can anyone tell if dl, just let me write. Whenever sine theta is there between two vectors, magnitude of two vectors are taken and sine theta is kept. So can you tell which product is it? Cross product, or dot product?
M cross product.
Cross product. Yes, it is cross product. So in vector form, if we represent it, dB, this is not used in your questions. See, more majorly in your questions, no, this will be used. This will be used. Your derivations, your questions, this will be used. This one for your numericals question. But in your exam, anything can come in your exam. It can come in terms of charge and volume and anything, velocity and anything that we'll discuss. So in vector form, dB is written in which way? dB is written as mu naught by 4 pi is there. Current I is there. We write it as r cube because we multiply the denominator and numerator with r. So that gives us LDL cross r. So your sine theta gets vanished over here. All right, this is your magnetic field in terms of vector form, your Biot-Savart's law vector form. Now this topic is important. The upcoming topic is important. This is the direction of magnetic field. The direction of magnetic field. So remember, direction of magnetic field is perpendicular to your DL and R, both of it. And we'll mostly use right hand thumb because different rules are there. This left hand rule, that left hand rule, that thumb rule, and different rules are there. It gets confusing ultimately. So we'll be using only our right hand. So that you should remember that only right hand is used, so you do not get confused. Or if if any rule is suitable for you people and you've been using it, so then that's okay, because direction by sign convention, it will come out to be the same. Even if you use it by a different rule and I use it by a different rule, ultimately, if the magnetic field is pointing outwards, it will come out outwards by my right hand thumb rule as well as your whatever new rule. But as a unity, since we are doing it in class, I'll prefer we all should go by right hand thumb. I discuss all the methods of it. So direction of magnetic field, remember, this is perpendicular to DL and R. Remember, DL is the current element, R is the position vector, and this is given by many rules, but we'll study right hand thumb rule. Palm rule is also there. Various rules are there. Various rules. It's just that at the end we get confused. If you have so many rules, you will be getting confused. Like your forefinger represented this in some rule, and that represented other in another rule. And right thumb is representing something. Left thumb is representing something. So that becomes confusing. That's why I'm preferring right hand thumb rule. So let's discuss two methods for it. Method 1. Let's say this is a wire flowing, this is the current I flowing. You have to hold the wire in right hand such that your thumb points in the direction of the current. See, I'll write it down. Hold wire in right hand. Firstly, remember right hand. Don't ever take your left hand for the right hand rule, because many times students, what happens is most of them are using their right pen for noting down everything. In examinations, I have seen many students doing this. Whenever they are writing in their copies in the examination, they are using their right hand for the writing portion of exam, and for the calculation of direction, they ultimately use left hand because it is free that time, and apply the conditions for right hand. So always be sure whether you are using your right hand and left hand. So hold the wire in the right hand. Such that the thumb points in this direction. This will be the direction of thumb. This will be the direction of thumb, like this. This will be the direction of thumb. If it is upwards, the direction of thumb will also be upwards, such that thumb points in the direction of current. Now the curvature of the finger will point along the magnetic field. Whatever is the curvature of the fingers, no, whatever curvatures of these fingers are having, these curvatures, this will give you the magnetic field, direction of magnetic field, whatever is the curvature for it. Like if you hold the thumb, then you will be having your fingers in this way. Your fingers will be here placed like this. So that curvature where your finger is moving, that shows the complete direction of magnetic field. So this is what curvature of finger points along magnetic field. That is P. So let's discuss this. I have taken this. This is the current. And I have taken this point A. Now take your thumb along the direction of current and tell me at this point A, what is the direction of your curvature going? Is it going outward? Is it going inwards? All of you text me. Just try it and tell me at this point.
I'm outward.
Yes, yes. Who answered this? Zed?
Yes.
Others? Did you get it? How outwards? Just place your thumb along with it. Place your thumb and see the direction of the curvature of your fingers. The direction of curvatures of your fingers at this point. And remember, this dot is represented for outwards. Okay, this point. Try this point.
I'm cross, inside, inward.
Cross inwards. And for inwards, you have this symbol inwards. Because representing or drawing all the lines outwards and inwards is not possible in 2D. No, we have 2-dimension figures. Your screen is 2D. So that's why it's better we use inwards and outwards symbols. So inwards it is cross, means your magnetic field is going. See what has happened. You have held the wire in right hand, that your thumb points in the direction of current, means your thumb must be pointing outwards, means upwards, your thumb will be upwards, and the curvature of finger, this will be in this way. Here your thumb will be there, and here your fingers will be there. So what will happen? If you use your right hand, don't use the left hand. If you people use the left hand, then your fingers will be opposite. Here you will get out inwards and here you will get outwards. Place your thumb along the screen. Whatever device you are using, if you're using mobile phones or using laptops, place your thumb in front of the current which is flowing. Like your thumb will be in this direction. This will be the direction of thumb. Like this, pointed. And see the curvatures of fingers for the right hand, that they will be inside right now, moving inside. So here it will appear that your current is going here and it is coming from this point. So it means at this point A, if I take it is outwards, at this point B, it will be inwards, using right hand. See your fingers, if you take the point B, no, it will see that your fingers are going inside the page. And for taking this point, your palm will face towards you, thumb will be upwards, and your fingers will be moving towards you. That shows outwards. All of you try right now. Okay, apart from this was first example, no. Now, don't unmute yourself and answer this part. All of you will write it. This is the direction of current. This is A point now. This is B point. All of you try this. Take the right hand, point your thumb, your nail should point towards the direction where the current is going. Like here, your nail is pointing upwards. Yes, Zed. Apart from Zed, others also try this. Anya, Khalid, Samaira, Sneha. If you're not able to understand, just ask me. I'll repeat it. But at least try. On your screen, whatever device you're using, mobile phones, laptop, place your thumb. And see at the point B what is happening, at point A what is appearing. Yes, Samira, that is right. Perfect. So Samira and Zaid have understood. Okay, Hania, I'll explain. So Hania has a doubt. Sneha and Khalid, you also try. Okay, class, I'm explaining this again. See, but when I'm explaining, perform this at your home, wherever place you are studying this. Perform this simultaneously, then you will be able to understand the direction. First, I'll explain this again. This is A point. All of you who all are having confusion, who all have done it as well. In front of the screen, place your thumb. Direction of current is where? Direction of current is upwards. So in front of the current, place your thumb parallel over there in front of the screen. The way you give thumbs up, no? Hania, Sneha, are you people trying it simultaneously?
Yes, ma'am.
All right. Now see, at this point I'm taking. See, when you will place your thumb, no? This will be the direction of your thumb, like this you must have seen. And these will be the curvatures of your fingers. Like this, is it happening? Hanya and all those. Was that Sneha and others also? Yes. Now see. Now just see what is happening. Your fingers are like this at this point A. Fingers are like this. Means they are appearing to come out. See, you're using your right hand. No, be sure about your right hand. You're putting your thumb in front of the wire. That is your current. Nail is pointing upwards. Your four fingers are they appearing to come out of the page? Try once again. See, if you place your thumb over here, your fingers, this is somewhat your palm will look like. Palm is pointing towards you right now. Fingers are closed. Look at the curvature of finger. Is it going outward or inwards right now? At this point. And what about Sneha? Just try at this point. If you're not able to understand, I'll explain again. With a different explanation, I'll explain again. But just try at this point. If you're keeping your thumb in this manner, your fingers are pointing towards you or towards the page. Then you just look at the nails. Nails are coming towards you or nails are moving towards the page. Sneha. Exactly, towards you. So you are where? You are, if it is pointing towards you, it means magnetic field is coming out of the page. That's why we have written it as outwards. Now look at this point B. Again, keep your right hand thumb only there. And now see the curvature of your finger. This time when you will put it, this will be the direction of your thumb. Thumb will be pointing upwards along with this current. See at this point B, where the curvatures of fingers are leading. Towards you or moving inside the page. At this point. Exactly. This is moving inside the page. Now, just to show this is outwards, we put a dot, and to show inwards, we put a cross. Now, come to example 2. This example. Now, you go try. Now, your current is flowing downwards. So, for A point, just try. Place your thumb there. Right hand thumb over there. See at A point what is happening. If you're placing your thumb downwards, at this A point, what is happening? Are the fingers pointing towards you or the fingers are moving into the page? Just see at this point. Here the current direction has reversed. Now you don't have to take it in this way. You have to take it opposite. It will be yes, Hanya. And Sneha, correct, perfect. So this will be inwards this time. And now see at B point. Now try for B point. Right hand, thumb pointing downwards because this is the direction of current. Yes, Khalid, correct. And Sneha, perfect. Hanya, outwards. Exactly. This will be across and it will show outwards. Now, is it clear to all of you? Answer with a yes or no. Yes, clear? All right. All right. So this is how you find out the direction. Clear. So just note it down. So let's just note. In your notebook also you can draw and then try, because shifting the notebook page is easier, no? Shifting the laptop or your mobile phones, that is difficult. But if you write it in your notebook, you can tilt the notebook as per your convenience. Now, method 2 and other examples, I'm not moving because my camera is not working today. So in the next class, I'll be opening my camera, and that time it will be clearer how to apply all these stuff, because just by dictating, no, and you people doing it, it is becoming difficult for dictating exact points. But what will be used is the cross product will be used in this chapter a lot, in the vector form especially. So revise cross product. Cross product you people must have done in 11th standard. No, a vector is there, b vector is there, making an angle of theta. So a cross b, this is given by magnitude of a multiplied by magnitude of b sine theta. That is the angle between the two vectors. And clockwise, start moving and take it as positive, and anti-clockwise take it as negative. Now, what to take it as positive, what to take it as negative, where to move anti-clockwise. This is basically if I write I cap, j cap, k cap. Now start moving from clockwise. So let's move from here. So k cross I cap. This gives you positive j. That's what I'm writing positive. This gives you positive j cap. Just a revision. I think most of you people must be knowing this. Just a revision for all those who have forgotten, because cross product is used in this lesson, especially in Biot Savart. Then I cross j. I cross j gives you this, whatever is left, k cap, with a positive sign because we are moving clockwise. J cross k gives you I cap. So all these are positive. If you move anti-clockwise, j cross I, that gives you minus k cap. If you move from I cross k cap, this gives you minus of j cap, and the last one, k cap cross j cap. This gives you minus of I cap. All right, so just note it down. This will be in your notes, and revise cross product, because in vector form of Biot Savart law it is used, cross product is used, and many a times direction is given, like dl is given as I cap and your r vector will be given as k cap. So I cap cross k cap will give you minus j cap. So these things should be specified. So just note it down. As all of you will write it down, just text me done. This is the last